In this lesson, we're going to be answering what is work. We're going to be using the equation work equals FD to solve problems. We're going to be talking about work done, units in direction, and then what happens when work equals 0. Work, W, is the energy transferred to an object when a force acting on the object moves through a distance. So work itself isn't really energy. It's not really a thing. It's the thing that transfers energy from one thing to another. So for instance, if you lift a box, you're going to transfer energy to that box. So the work is the actual transferring of the energy from you to the box. By the time you're done, that box has energy, usually energy of position if you're lifting it up. So if you're going from here and the box is on the ground, you have energy. You have energy from the food that you eat. You have energy in your muscles. So when you put energy into the box, you lift it up. So you're going to lift the box up to a certain height. When you do, this box now has energy of position. Energy of position means that if you were to let it go, it would fall. It would fall from here to here. It has energy based on its gravitational position relative to the ground. If you were to let it go, it would hit the ground. Now the equation we use to solve these problems is W equals FD. F is going to be the force acting on the object parallel to D, and D is the displacement, so how far the object moves in that same direction. Work done. Work is done when you lift an object. So for instance, when this guy lifts up the barbell from here to here, work is done to that barbell. Work is done to a bow when you bend it, and work is done to the arrow when it's fired. So when you bend the bow, you go from the bow being like this to like this. That stores energy inside the bow. When you release the string at the back, that transfers the energy from the bow itself to the arrow, giving it energy of motion, otherwise known as EK. And work is done to make a car accelerate by its motor. The motor spins, it causes the tires to turn, causes the car to go forward. Work. Now consider a situation where you're pulling a bag on wheels at an angle theta to the displacement. The force parallel to the displacement equals force cos theta. Because remember, our force is going to be the force parallel to the displacement. So since we're walking in the right direction, and our force is going to be up at an angle, the actual force directed to the motion of the object is going to be force cos theta, okay, because that is in the direction of motion. Force cos theta is going to the right, and so is our motion. So the only force that we are concerned with is the force parallel to the direction of motion. Check your understanding. How much work is done if a suitcase is pulled at an angle 30 degrees above the horizontal with a force of 15 newtons, a distance of 10 meters? So let's draw our free body diagram. So that's our suitcase. We're going to be pulling it at an angle of 30 degrees with a force of 15 newtons. And we're going to move that object 10 meters. Now our equation, work equals force times distance. The force in this case is going to be 15 cos 30, because we're only going to be concerned with this part right there. So that's F cos 30. And then we're going to multiply that by the distance, which is 10 meters. And when you do the calculation, you get 129.9 Newton meters, because we have forces in newtons, and the 10 is going to be in meters. Now we need 1 sig dig, because we have the 30, so it really should be 100 Newton meters. Now we're going to look at a different unit in a second, but for now 100 Newton meters would be correct. Units in direction. Work is a scalar and has no direction. Now we just established that it was in Newton meters our answer, but Newton meters is actually the joule. So we're going to refer to our answers in joules from now on. Now 1 joule is going to equal to 1 kilogram meters squared per second squared. So keeping in mind we need to have everything in kilograms, meters, and seconds. Positive or negative work. Now if the force and displacement are in the same direction, work is positive. If force and displacement are in opposite directions, work is going to be negative. Now what does this mean? Well, work is positive, negative, or zero depending on the angle between the force and the displacement. Pretty much that if the angle is less than 90, we're going to be putting our force in the same general direction as our displacement. So in this case, you can see that we can get a component of force going to the right. When theta equals 90, we're going to be working in perpendicular to our distance, and that's going to give us a work of 0. We're not actually going to do any work on that object. And when theta is greater than 90, our force is going in the opposite direction as our displacement, and it's kind of working against us, because our component would actually be to the left, giving us a negative F value. In either case, it's always going to be F cos theta. And if you want to make no mistakes, just put F cos theta, and then if theta is 0, as in the force is in the exact same direction as the displacement, then it simply becomes F cos 0, which is simply going to equal to F. Now we can try this as well. So let's just say our theta was 30 degrees, our theta is 90 degrees, and our theta is 120 degrees. Now if we put these into our calculator, we're going to get very different values. For each case, let's use a force equaling to 10 newtons. Now in our first example, the work is going to equal to the force, so 10 cos 30. which is going to equal to 8.66 joules. In the second example, our work is going to equal to 10 cos 90, which is going to equal to 0. And in our third example, our work is going to equal to 10 cos 120, which is going to equal to negative 5 joules. So you can see when our force is in the same direction as our displacement, we get a positive number. And when our force is perpendicular, then we're going to get a 0. And when our force is greater than 90 degrees, we get a negative number for our work. Now, an example of this, where the force is in the opposite direction of motion, would be things like friction. A practical example would be brakes on a car, etc. Now, if velocity is constant, isn't acceleration 0, and therefore F equals 0 and work equals 0? Well, whenever you talk about the work done, you got to be very careful about what force does the work. So for instance, if the object is moving at a constant velocity, the work of friction is going to be F friction. That's going to be 10 cos 180 because it's going to be opposite direction times 1. Let's just say the distance is 1, and we get negative 10 joules. So the work done by friction, even though we have a velocity is constant and our acceleration is 0, we still get work done of negative 10 joules. Now the work applied is going to be 10 cos 0. We're going to be pulling forward directly with a force of 10 newtons over 1 meter, and that's going to give us positive 10 joules. So again, even though our acceleration is 0, we still get a positive joule number. So even though we do not have an acceleration, we still get a value for our work. Now the net work, however, that's when it comes out to 0. So the F net, remember the sum of the forces, is going to equal to, in this case, the force applied minus the force of friction, which is going to equal to 0 because A equals 0. In this case, the net work is going to be equal to 0. So keep in mind that even though the net work is 0, there's still work being done on the system. Check your understanding. A grocery store employee is pushing a line of carts at a constant velocity, so V is constant. And if V is constant, we know that A equals 0, with a horizontal force of magnitude 95 newtons. So force is going to equal to 95 newtons, and we'll call it that way. How much work is done pushing the carts 16 meters, in the direction of the applied force? Express your answer in kilojoules. So W equals FD. The force in this case is 95. The distance is 16. And that comes out to 1,520 joules. It does say to put it in kilojoules, however, so we're going to need to divide this answer by 1,000, and we get 1.52 kilojoules. Our answer should have 2 sig digs, so our final answer needs to be 1.5 kilojoules. Check your understanding. 2,000 newtons of force is applied to a cable used to tow a car 20 kilometers. So force is going to equal to 2,000 newtons. The distance is going to be equal to 20 kilometers, which is equal to 20,000 meters. How much work is done? Work is the question. Work equals FD. Force is 2,000 times the distance, which is 20,000. And that equals to 40 million joules. Now we're told that 1 million joules equals 1 megajoule. So we're going to divide that by 1 million. And we're left with 40.0 megajoules. 40 because we have 3 sig digs there. Check your understanding. A customer moved a 4.4 kilogram box without acceleration along a shelf by pushing it with a horizontal force of magnitude 8.1 newtons. So let's draw that out. So there's our shelf. There's our box. We're going to get a force applied equal to 8.1 newtons. And the box is going to weigh 4.4 kilograms. And then we're told that acceleration equals 0. Therefore, it's going to be constant velocity. If the person did 5.9 joules of work, so work is equal to 5.9 joules of work, how far did it move? Now, distance is our question. So work is going to equal to F times D. D is going to equal to W divided by F. The work we're told is 5.9 joules. The force is 8.1 newtons. And when you divide them out, you get 0.73 meters. A sled carrying 2 children, total mass 85 kilograms, reaches its maximum speed at the bottom of the hill, then glides to a stop in 21 meters along a horizontal surface. The coefficient of kinetic friction between the toboggan and the snowy surface is 0.11. So let's try that out. So we're not interested at all about the hill. We're interested in what happens after it reaches the bottom of the hill. So let's draw that out here. So we know that the mass is 85 kilograms, and it's its maximum speed. It then glides to a stop in 21 meters. So this is where the toboggan stops. The coefficient of kinetic friction, so mu k, is 0.11. And we're interested to know a few things, including the free body diagram and the magnitude of the kinetic friction acting on the toboggan. Because that's the only thing that's going to slow the toboggan down. It's going to be the friction acting against the motion. So if we draw a free body diagram, we know that we have an FG, we know that we have an FN, We have no applied force because the only reason it's moving is because it went down the hill, but it has energy at this point. And we're going to have kinetic friction acting against the motion, eventually slowing it down. So that's our A. As soon as we put in our positives. Now our B says determine the magnitude of the kinetic friction acting on the toboggan. So B, Fk is going to equal to mu k times Fn. Mu k we're told is 0.11. Fn is going to equal to Fg, which is going to be the mass, which is 85, times 9.8, which equals 91.63 newtons, negative, because we know we're going to the left. And since we said right was positive, left would be negative, we're going to say the answer is 92 newtons to the left. Now we're going to add another component to this question. We're going to say calculate the work done by the kinetic friction. So now we know, right, we have our sled. We know that the friction is working backwards. We know the motion is to the right. So when we say work is going to equal to F times D, the force we know is going to be 92. Cos, now completely backwards, is 180. And we're going to multiply all of that times the distance that it takes to stop, which is 21 meters. And that gives us an answer of negative 1,932 joules. Now it's a negative number because our work is going to the left in our case, and that's fine. We're almost done. We need to have our answer again in 2 sig digs, so our final answer becomes negative 1,900 joules, or negative 1.9 times 10 to the 3 joules. Check your understanding. A bag of groceries of mass 8.1 kilograms is raised vertically without acceleration from the floor to a shelf over a distance of 92 centimeters. So there's our bag of groceries. Our shelf is right there, and we're going to put our bag of groceries on that shelf. And that distance, we're told, is 92 centimeters, so 0.92 meters. And we're also told that acceleration is equal to 0. Therefore, the force up to raise it is going to equal to the force down. Now the force down is going to be equal to Fg, so we got to keep that in mind. Now we're asked first, what is the force needed to raise the bag without the acceleration? And that's going to be the force up. Now we're going to say force up is going to equal to Fg, which is going to equal to mg, which is going to equal to the mass, which is 8.1 times 9.8, and that gives us 79.38 newtons. We need 2 sig digs in our answer, so our final answer becomes 79 newtons up. B. What is the work done on the bag of groceries against the force of gravity? So now work is the question. Work is going to equal to force times distance. Our force is in the same direction as our distance, right? Our force is going to act up that way. Our distance is also that way. So we're going to say 79.38. We don't use the rounded number. Cos 0 times 0.92. And that equals to 73.0296 joules. And to 2 sig digs, it's 73 joules. No direction because it's scalar. Check your understanding. A student pushes against a large tree with a force of magnitude 250 newtons. How much work does the student do on the tree? So what we need to understand is that work is equal to force times distance, like we've talked about. The force we're told is 250 newtons. But what is the distance? Well, if it's against a large tree, it can be assumed that the tree is not going to move. So 250 times 0 equals 0. So when the student pushes against a large tree, no matter how hard he pushes, assuming the tree doesn't move, there's 0 work done. Check your understanding. A 500 kilogram asteroid is traveling through space far from any measurable force of gravity. So in this case, F approaches 0. If it travels 10,000 kilometers per hour for 100 years, how much work is done on the asteroid? So work is the question. Distance is going to be quite a complicated number. But the thing you got to keep in mind is that F is approaching 0. So F is going to be 0. So no matter what distance is, work is going to equal to 0 times a number. Anything times 0 is 0. So the work done is 0 joules because F approaches 0. Check your understanding. You're walking east at 30 meters a second while holding a box of mass 10 kilograms still on your shoulder. You walk 20 meters. How much work is being done on the box? So work is the question. Force is going to be the force required to keep that object up. Now if it's a box, force is going to be up that way because gravity is working down. But the thing to keep in mind is that distance is that way. So we're going to have to keep that in mind. So force is going to equal to the force to keep it up, which is going to be the mass, 10 times 9.8 times cos, and 90 degrees, which is going to equal to 0. The displacement is 20 meters, and when we put it in, work equals 0 times 20, we get 0 work done, once again. And the reason for this is the force required to keep the object up is in perpendicular to the displacement that the object travels in. So here's our summary. So when does work equal zero? Well, work equals zero when distance is zero, like pushing our tree or our big rock. Work is equal to zero when F equals to zero. Now it's hard to determine a time when force is actually equal to zero, but it's more like when F approaches zero, really. And that can be when a spaceship is so far away from anything in outer space that the force of gravity does approach zero. And lastly, work is zero if theta is equal to 90 degrees, like if we're carrying boxes and forcing the boxes up while walking perpendicular to that direction. And that concludes our lesson on work.